Hi everyone. I figured I'd do this video on bushings and bearings that are available to us in class. I always have the feel that some of the students walk away using bushings and bearings because they're told to, rather than have an appreciation for exactly what they do. So maybe a quick video on our use of these. So this is the sample of a bushing that would be available to us, and this one is a 1/4-inch bushing, and what denotes that is the ID, which is where the rod would go in. This happens to be a 1/4-inch rod, right? So that's how the bushing would work. And then the outside diameter is actually this diameter, not this larger one, but this one here, and that would determine the size of the hole that you would put in your part in order for that bushing to press in and remain in there, so that whatever rotating component that goes in your bushing has very little friction. The bushings are made out of nylon, and nylon is one of those materials that's actually been around since like the 1930s that has a very, very, very low abrasive property. Therefore, the friction is like nil. There's no need for lubrication on the nylon. So it's paramount that we use these in our design, because you would never want your shaft going through a 1/4-inch hole that it just rotates like this. There's so much friction in the aluminum on aluminum that that wouldn't be proper. And if that was compiled where it's in several different locations, the shaft wouldn't move at all. So what we do is we put the bushing into our machined hole, and that's the interface between the two components now, and you can see it's effortless. So that's what we use bushings for. The same thing goes with the bearings. These are the bearings we have. Again, they work in the same way. You have the ID, you have the OD. I don't think I talked about the flange on the bushing, but we also have a flange on the bearing here. And so how a bearing works, these are made up of 4 components. You have the inner race, which is this ring right here, and you have the outer race, which is this. And then if you look right inside here, right next to where these balls are on each side, you can see that. This is called the cage, and the cage is what locks the balls equally spaced about this diameter. So that when we rotate this, the balls just aren't loose, they actually are captured in a specific location. With the really nice thing and the biggest benefit of a bearing is that you have such low friction on these. The only friction that's there is actually what they call rolling friction, and that's basically where the balls are rolling in the inner and outer races of these. I actually made a quick drawing right here. I'm going old school on us here. You can see how you have the outer race, inner race, and the balls. And if I cut this in half this way and then look in here, this is called a cutaway view. You can see the arrows are telling me which way I'm looking. And I take this and I flip it up like this. I'm actually seeing the outer race, the ball, and the inner race on both of these sides right here and here. So you can see how the ball's sitting in that raceway right there, and that's what guides them. And very little friction. Excellent application for using those on our machines to essentially eliminate all friction on those. Give you an idea, right? You all seen a skateboard. So how a skateboard works, if this is the truck, we'll say, of the skateboard, right? I'm capturing the inner race of the bearing. That's stationary, that becomes part of the truck, and the rubber wheel of the skateboard is pressed into this bearing, and so as the wheel goes over the ground, right? You can see the outer race is rotating and the inner race is stationary. And that can be just in the opposite too. If I were to capture this and it were to be stationary, the inner race would be able to rotate independent. So that's really cool about the bushings and bearings. Very important that we use those. So I made up this little plate that's going to be available for your viewing pleasure, as they say, that shows you some of the applications used for the bushings and the bearings, right? The bushings are these four, the bearings are these guys right here. And you can see my shafts. They're all captured by these, you see these little black things right here. Those are the E-clips. And it's kind of difficult to see. We'll see if we can focus in, but you can see the E-clip. Let's see if I find a better one. The E-clip is sitting in a little groove that's, maybe this one here. A groove that's in the shaft, and that locks it in place so the shaft can't come out of the bushing and bearing. That locates it. So this will be available for you to touch and feel. Notice this one here, it has the hex shaft going into bushings. Well, how's that working? Well, what we've done is we've broached the hole. Now, broaching the hole is a process where I take, in this case, a 5/16 diameter bushing. That's the ID, right? That's how they're denoted. And I create a hex hole in that bushing that accepts the hex stock that we have available to us. Now, there's a lot of applications for the hex stock, right? That would be like anti-rotate. Whatever you put on here can't rotate because of the flats on the hex. Unlike a round shaft, right? You'd have to find a way to attach whatever it is you're looking to get on that shaft. So by taking a tool, we call it broach, and it's a progressive tool. You can see how it has all these stages, and as I push this through the bushing and I come out right the other side like this, what happens is I leave behind the hex, because every one of these stages removes a little more material until that hex is formed. And so what that gives us is it makes it so the bushings will rotate in our plate. Unlike this condition where they're stationary, our bushings can rotate, and I put little black dots on here so you can actually see that taking place. You can see how the hex shaft is rotating. So it makes for a great drive assembly because we don't want anything slipping, correct? That would be my guess. We'll move over to the bearings here. Kind of hard to see. I left the shaft a little bit sloppy so that you could see in behind there. But the shaft goes through the inner race. The outer race is captured by the plate. And if you just do these two side by side like this, you can really feel the difference in the friction. This is minimal, and this is almost non-existent. So that's the slight difference between the bearings and the bushings, but they certainly both have an application at some point in your design. This one here, I turned down the diameter of the hex material down to 1/4 of an inch to fit through the bearing. So there's another application, right? You can still use the hex material and use the ball bearings, and that's pretty cool. One last one I'll show. Now, the bushings aren't necessarily strictly for rotational motion. They can actually be used for linear also. So you can see how I have those bushings pressed in my plate, and then I have this shaft that's able to slide back and forth. Now, I'm not giving it any rotational. I could at the same time, but this obviously is a great way to reduce the friction between aluminum materials. So that's kind of neat. So there's an old saying, I forget, I think I can remember it. It was a bushing is a bearing, but a bearing is never a bushing. I guess, I don't know. I think it has to do with the fact that you would never want this sliding application in one of these, right? It goes against how these are assembled. These are basically rotational only, where the inner race you wouldn't want to apply pressure side by side with the balls. So anyhow, that's a quick thing on bushings and bearings, and I hope that helps.